Okay, a couple things regarding the homework. The first thing here is down in Moodle. I'll save the slides when we go over the homework. So that'll be down here. Statics recitation slides will be down there. So what I do after we go over the homework, I'll just save the slide set down there. If you want to look it over, that'll be there. Okay. So that's in Moodle. And then a couple little remarks on the format for the homework. Let's see here. All right, so that's what I'm looking for there on homework. Your name, the date, problem number, and page number. I want a sketch. Straight edge is a good idea. It cleans up the sketch and makes it look reasonable. Problem statement. And then the one thing on this, when you come up with the answers, put them all down at the bottom in a box so I can find them. Kind of what the deal is on that is, when I'm working through 30-some homeworks, I get kind of very systematic about how I do it. And I'll look for the answer, then I look through the solution. When the answer's in different places on the page, I kind of have to start scanning around. It just slows me down. So what I'd like is all the answers to one problem in a box, okay, at the bottom. The other thing is, for those of you that are online and you're uploading homework, I can't take JPEGs. They're too much work on my end to open them and to look them over. So scan your work as a multi-page PDF. You can either get on a scanner and scan as a multi-page PDF. There's I think it's called Cam Scanner or something. There's apps you can get for your phone that'll do it. If you need to, you could even scan as JPEGs, put them into a Word document, then do a save as a PDF. But however you do it, I need the homework uploaded as a multi-page PDF because it's difficult for me to work with JPEGs on my end. Okay, so please remember that. All right. So that's just a bit on the homework. Okay. All right. So we're going over this 3D vector stuff. We've been doing that. Might be worth a quick look here. So let's see what we did on this. So we're going into 3D now, which is a little bit more, I use what I would call a more formal approach on this stuff and how I do it. So what we found out there was that on this problem here is that if you know the angles that a vector makes with the three axes, you can come up then with the unit vector. So what we did on this example here, this is in the packet of course, is we went through a basic example of that to turn, if we knew the magnitude of the vector and we know the angles that the vector makes with the x, y, and z axes, we can run through a process where we can generate a Cartesian 3D vector. So I'm on page 180. All right, and the process basically is like that. So you look at the angle that the vector makes with the three axes. You take the cosine of the angles with the x, y, and z axes. That gets you the unit vector. You then factor that vector up by the magnitude of the force. That gets you the force vector. Okay, that's how you take a 3D vector with angles and a magnitude and turn it into a force vector. Then later on, we went into two special cases. The first one is this one here, where and what we're starting to get into with this is the meaning of those dashed lines, because what you're doing here is drawing up a 3D vector on a flat piece of paper. So you have to use conventions to draw that up. So that requires that you start to learn how to read the conventions. The main convention here is that a dashed line what that represents is a parallel line to one of the axes generally. So you'll see that line that I'm now highlighting in green is parallel to the z-axis. What that means is point A is directly below the x-axis in the z direction. So if you start at the x-axis, go in the negative z direction, you will end up on point A. So that means that that vector that goes from the origin to A is in the xz plane. That allows you then to get the three angles. Alpha is 50 because it makes a 50-degree angle with the x-axis. There is a 90-degree angle there between the x and the z. The 50 and the 90 are coplanar, so you can add them up and get 140. That's gamma. Okay, that's the angle with the z-axis. And being as the vector is in the xz plane, the angle from it to the y-axis is 90. Doesn't matter where it is in the xz plane. It will make a 90-degree with the y-axis. Once you have that, you can do cosines for alpha, beta, and gamma, the angles with the x, y, and z axes, and factor that up by the magnitude of 400. So, we all right with that? Questions? Good. All right. All right, the other special case we came up with then was a double projection, a little bit more complicated. It again uses these dashed lines. So what you have for that example there on the bottom of the page, I'm on page 190, is that you've got that one dashed line going from the end of F4 down to the plane. That is parallel to the z-axis. You then have a second dashed line that goes from point B over to the x-axis. That dashed line is parallel to the y-axis. All right, so that means you've got some right triangles to work with then. So what you're going to do with that is you're going to project that vector first down to the xy plane. That gets you down to point B, and that's a right angle there, so you can use a right triangle relationship with that right angle right there to get that projection in the xy plane. That'll be based on cosine 32. And then once you've got it there, you can go cosine of that. I think it's a 20-degree angle to get it over to the x-axis. Okay, so to get the x component of F4, you go F4, its magnitude, times cosine of 32. That gets you into the xy plane. Then cosine of 20 will get you over to the x-axis. It is 20, isn't it? Yeah, it is, okay. So you can see how that projects down into the xy plane. To get to the y-axis, you got 20 plus 90 more, that's 110. So that's F4 times cosine 32 times cosine 110. That will get you the y component. Now, of course, the y component will be going that way, won't it? Okay. So that's the y component. So that'll be a negative component. And then to get the z component, you've already got 32 to get into the xy plane, so 90 minus 32 gets you 58, and that's up onto the z-axis. Okay. So that's how we've been working with these 3D vectors here so far. Do we have any question on that process there? You doing all right? Okay. All right, and what problem 143, which will be due this Friday, that will reflect this type of problem here, I think. Okay.
Can we look at the sketch for 143?
Yeah, sure. There's 143.
Yeah. So is that 41-degree angles from the y-axis, negative y-axis?
No, it's to the x. So what's happening here with this is the homework problem that you'll be doing.
So 72 is to the y-axis.
No, the 72 is from the vector to the xy plane. So what's happening here is I'm starting at this point and I'm going down. So that line goes straight down. That's parallel to the z-axis. Then I've got a second projection line here that's parallel to the y-axis. Okay? So what that's telling me, if I start at the x-axis and go out, this point here, which I didn't name, but that point there is in the xy plane. So there's a 90-degree angle right there. So I can project F1 down into the xy plane. Once I've got it there, I can use that 41-degree angle, which is the angle between the projection that we just went over here in the xy plane and the x-axis. So the 41 is to the x-axis. And if you have a look at that, you'll see it connects the vector to the x-axis. Okay.
So if we're supposed to find FR, which is the resultant of like F1 plus F2 on the XY
Mm-hmm.
Z, is that 41 degrees alpha for F1?
It's not alpha quite. No, you have to do a double projection for that. So you don't have alpha or beta or even gamma for F1. You have to kind of work through that.
Okay.
And so to get the x component, you're going to have to go cosine 72 times 2000. That will get you into the xy plane. And then take that vector in the xy plane and use the 41 to get onto the x-axis. You have to do two steps. Okay? So you're not given any of these angles directly. That's all like 1, 2. The z-axis, you're kind of given that angle. You can figure that angle out pretty quickly. But for the x and y components, you got to go down to the plane, then swing over to the axis. It's a two-step process. It's called a double projection. Okay. You all right with that? Good. Other questions? Yeah. All right, so that's the one that'll be due Friday. We can go over it a bit next time too, if you run through it and have questions. All right. We're good. All right. All right. So that's one way to do vectors there if you have angles. But as it turns out, it's not the most common way, because when you start doing engineering plans, they're not going to put a bunch of angles on there if you look at blueprints. It's just too complex to do. What they're going to do is give you coordinates. Generally speaking, when you're dealing with a set of engineering plans, it's on a coordinate system, X, Y, Z. So this strut here that's holding up this building, you'll be able to figure out this coordinate and that coordinate. So you can get this vector. And if you have that vector, then you can work into a force vector for that strut that's holding up the roof. And that's done with position vectors. Okay, there's a conveyor. See how readily that goes into an X, Y, Z coordinate system? I don't know quite now how you might go X. You could set these up differently. You'd have it set up in your computer. There you go, X, Y, Z. You would work with coordinates on that, okay? So that's normally how you set up engineering plans on a coordinate system. Okay, if you have the frame that goes into that vehicle, you're going to have coordinates on those points, X, Y, and Z. And that's how you're going to work with it. So let's have a look. I think it's page 195. And why don't we have a look at how to work with that, okay? All right, now a coordinate, it's kind of expressed two different ways. You can have a coordinate which is just X, Y, Z. Now what you have on this particular problem here, or this particular coordinate for point C, is you go 6 in the X, so that's a 6. And then you're going, looks like -1 in the Y, so that's -1. And then you're going up 4 in the Z, so that's the 4, okay? So that's how I'm reading that coordinate system. I'm using that same convention with dashed lines to indicate direction there. So 6 in the x, -1 in the y, 4 in the z. Okay. Now I can express that in different ways. I can call it out as a position vector, which would have an I, j, and k component. So 6i minus 1j plus 4k. Sometimes I just call it out as a coordinate too, as you would in math, 6 minus 1, 4. Okay. You could do it either way. So we all right with that? Okay. Yeah, let's see here. All right, why don't you look at those two and come up with coordinates for A and B? Why don't you everyone just do it on their own and write down the coordinates of A and B? So just look at the lines and what they're parallel to. That's how you figure out the direction of the lines. We're starting at the origin and going to A, and we're starting at the origin and going to B. Okay. What do we got going on for A? 5, 8, 1. Is that all right? Good with that? Okay. And that's kind of easy because you just do them right in order. You got X, Y, Z. You do want to double check these as you're going through them because they're not always dimensioned in a nice straight X, Y, Z format. So like B is actually what? -8, right? For X, because that's going in the negative X direction. 3 and -2. Y'all okay with that? -8, 3, 2. Got any questions on those? This is a skill you want to have. You want to be able to read these coordinates.
Is it -2 or positive?
It's negative because what's happening there is we're kind of going up on a pathway. We're starting from the origin, so we're going to the right with 3. Now that's 3y. We're going back in the negative x direction, so that's the -8, and then we're going down from there. It's difficult to draw this stuff in 3D. That looks like it's above the y-axis, doesn't it? But even though so, it's drawn down because it's got a perspective going into the board. So you have to kind of look at the direction of the lines, not the position in space, because they're going to be quite deceptive. Okay.
Oh, yeah.
You kind of think of taking a walk, walking along that line. And again, it's hard to draw a 3D on a flat piece of paper. It can be a little deceptive where those points end up. It's not as simple as 2D where you can just look at where the dot is and infer it from that. You kind of have to follow the path to get from the origin to that point. Okay, we good with that? All right. And we got one other here. So this is, the title of this one should be Don't Overthink It. So what do we got? What's that one? Yeah, 3, 6, 0. See, there isn't a Z component. Okay? So that one's in the XY plane. Okay? So, you all right with that? Good? You just want to be able to read these. It's just like a dimensioning system. Not quite what you learned in drafting, but it's a similar idea, okay? All right. All right, now we'll apply that a bit. So let's do a little bit more on page, whatever it was, 195, I think. So let's go back there. All right. All right, now, quite often, see, if you have a full set of plans, you can't guarantee that you're always coming from the origin to measure a distance or a line. You might work from one coordinate to another. So I've got points A and B there. And let's figure out what RAB is. Okay, so that's RAB, meaning R, the position vector. R is what's used for position vectors, starting at A and going back to B. So that line would look something like that, okay? All right, now let's have a look here. Let's start by getting the coordinates of A and B. So why don't you get the coordinate of A, RA, and RB. It looks like I forgot a vector hat on this one. I don't know if that's the case in your handout or not, the packet or not. I don't know if I fixed that or not, but I don't know, maybe that ought to have a vector hat on it. So start by getting those filled in, and then look at how you go from A to B. Now, how do you get there? So I got RA at 2 minus 3 minus 1, and I got RB at negative 162. Okay, is that good? So now the next little thing is, how do we get from A to B? In the X direction, how far back do you go to get from A to B? In the Y direction, how far ahead do you move? In the Z direction, how far do you move up? Okay, that's how I get from A to B. And again, when you have a set of plans, you're going to have coordinates on everything. And so this is how you're going to work with them. So you're going to go from one to the other. You know, I've done some surveying. I'll have my survey instrument on A. I need to set point B. I have to know how to get from A to B. I want a big piece of ground with coordinates on it, okay? All right, so to get from A to B, what do we do? In the X direction, we're going to go back 3, right? Because in the X direction, we're going back 2, and then we're going back 1 more. So that's back 3. Good with that? The Y direction, what are we doing? We're going over 3, and then we're going over 6 more. So that gets us 9. Okay. And then in the Z, going up 1, going up 2 more, that makes 3. Okay? So that's how I get from A to B. So I can make that a vector. It's minus 3i plus 9j plus 3k. As I've mentioned, if you want to write them out like this, that's fine with me, and I often do that because it's quicker, it's faster. So we doing okay? Now, this is how you look at it. Now, there's a way to compute it that's a little bit more systematic. So let's look at how to compute it, okay? And this is on your formula sheet, and we want to get this straight. When we want to find RAB, we take RB minus RA. You have to remember to switch the letters around. So to get from A to B, you start at B, then take A away from it. So that's the order of subtraction. That's on your formula sheet if you ever have questions on it, okay? So as I mentioned, I like to subtract in columns, so I'll put RB up there, then take away RA. So I get -1, -2 is -3 for the I. 6 minus a -3, so you got to watch your signs on this, is 9J. 2 minus a -1 is 3K. All right. And I just did it with the IJK stuff on the left and without the IJK stuff on the right. Again, I don't care how you do it. Doesn't make any difference to me. Whatever works. Now, I do want to point one thing out, and I always like to kind of point out study tips and all that. If you're on a test, don't do these in your head for two reasons. One reason is you might make a mistake, because when we do things in our head and we're in a bit of a rush, sometimes we make mistakes. And the second reason is if you make that mistake and you're doing it in your head, I don't know what you did, okay? So remember, when you're doing homework, and especially on tests, leave tracks. Don't overdo it, but if I see those numbers and you make a mistake, I'll go, oh, you made a mistake, made a math error, arithmetic error. That's a point off. But if I get this vector and I have no idea where it came from, that's a different situation, okay? So leave tracks. That's how you take a test. You make sure somebody can grade it. You kind of do that. What do they call it? Is that metacognition? Is that the fancy word for that? I think it is, but I'm not sure. That's got more than 2 syllables, so I don't know if I can handle that one. But anyway, that's the idea. Be thinking about what I'm thinking about when I grade it. Just don't overkill it, but leave tracks. Okay? All right, so we good? Okay, so let's do a little force problem here. Let's say we've got our truck stuck again. Okay. Now we got a winch, we're gonna tie off to a tree, and we are going to try and pull our truck out. Okay. Let's express FAB as a Cartesian vector. Now, being as this is the biology building here, we're gonna be more concerned about the tree than the truck. So we're gonna look at the force that's exerted on the tree, 8,000 newtons. Okay, that's what's happening to the tree. So let's try and make that into a force vector. So for starters, let's get coordinates. Get a coordinate of B and a coordinate of A. The coordinate of B and the coordinate of A. So we get those coordinates first. And what you notice over there on the left is I have the steps. And that's how we like to think about this 3D stuff, is a series of steps. So the first step here is to find the coordinates of A and B. So -2, 0, 1 for B, -4, 12, 5 for A. Is that good on the coordinates? Okay. Now I'm looking at from the perspective of the tree and how that cable is pulling on the tree. It's got a magnitude of 8,000, and so I want a position vector. I'm going to work and try and make that into a force vector. So I want the position vector from A to B. So I'm going to take what? B minus A, right? So let's line up B, put A under it, subtract it, and get the position vector that goes from A to B. And then after we do it, we look at it and make sure that it makes sense, that it looks reasonable. Okay. So we want RAB. Good. So to get from A to B, are we going 2, -12, -4?
When do you know to put the negative on A?
You always do, because you're doing B minus A. So I put RA in parentheses, put the negative outside, it carries through. So -2 minus a -4 gets me +2, 0 minus 12 gets me -12, and 1 minus 5 gets me -4. Does that look about right? Okay, now that's how I'm getting from A to B. So positive X, a big negative Y, and a negative Z. I'll look at my sketch, positive X, yeah, big negative Y, yeah, negative Z, yeah, that looks good. Okay, it's looking about right. All right, now the unit on that is meters. That's a position vector, so it's expressed in meters. All right, now let's find the magnitude of that vector. So to do that, we'll take the square root of sum of the squares. Okay, let's do that next. So we'll find the magnitude of that vector. Okay, so you just want to take square root of sum of the squares. Now remember, when you take those squares, all the negatives will square out. I go ahead and put them in there. I want the negatives in there because that way when I carry through, I remember that they're negatives, but you know, that'll come out. I got 12.8. Okay, units on that is meters. Now in the physical world, what is that? What does that represent? It's the distance, yeah. It's how long the cable is, yeah, right, okay? So that's how long the cable is. All right, now, we good with that? 12.8? Now the next thing I want to do is I want to get a unit vector, okay? Because to get a force vector, I need a unit vector. So to get a unit vector, I take the vector AB and I divide through by its magnitude, which is 12.8. And you know what? I've got a typo there. That should not have a vector head on it. So I screwed that up. Because that's a magnitude. That's not a vector. That's a magnitude. So that ought to go away. All right, so RAB is 12.8. I'm going to divide through by that now, and that will get me a unit vector. See, when we're doing the angles, we did the what? The cosine of the angles to get the unit vector. Now we're getting the unit vector a different way. We're taking the position vector and dividing it by its own magnitude, its own length. Because I know, see, that position vector, RAB, has a magnitude of 12.8. If I divide each one of the components by 12.8, I get a unit vector, see? So this is a different way to get to a unit vector. So that unit vector is 0.156, -0.937, -0.312. It points in the same direction and has the same XYZ proportions as the RAB. It's just now it has a magnitude of 1. So I think of that as being like a direction pointer. It points from A to B. Okay. And I checked that. I just took the square of each of the components on the unit vector. They, when I add them together, I got 1. So that's good. Okay. So that is indeed a unit vector. Okay. So now I got the unit vector. See, now what we did last time is we used the cosine of the angles, but this is another way to do it. I'm taking the position vector and dividing through by its own magnitude, okay? All right. Now, if I want a force vector, what's the next thing I do here? Scale it up by what? By 8,000, okay? And see, that'll keep the vector pointing the same direction, but now it'll have a magnitude of 8,000. So what I'm doing there is I'm taking that position vector, I'm taking the length of the vector out as a magnitude and replacing it with the magnitude of the force. And that ends up getting me a force vector that points in the proper direction, okay? I don't want the length of the cable in there. That doesn't affect the force. I want to get that out. And then once I do that and get my unit vector, then I scale it up by 8,000, okay? And that will get me the force vector. So that's the force vector that's pulling on the tree, is what that is. Okay. So that's the process. That's a very common process that we use a lot in 3D. This is often the starting point for when we work through problems, is we want to find a force vector. So that's how you do that. Okay. So we're good with that? We got any questions on that process? All right. Now the last little bit, if I want to know alpha, beta, and gamma, if I got the unit vector, those are the cosines of the angles, so I do the inverse cosines of those unit vector components, and I get the angles. Now there's actually two ways to write that. You could also write that cosine to the -1 of 0.156. That's another way to do it. They mean the same thing. I've seen calculators with both buttons on there. So cosine to the -1 is the same thing as what's called the arccosine. Okay, same thing. Inverse cosine.
The unit vector.
Right. Yeah, you're using the unit vector. You're taking the inverse cosine of the unit vector components. So if you want to know those angles, that's how you get them. So that's a little thing you do in 3D there. Yeah, question there?
The Greek letter for the Z, what is that one called?
Yeah.
Okay.
Alpha and beta are easy enough to see. I don't know quite, obviously alpha turned into a letter A and beta into our letter B. I'm not sure how gamma turned into a G. It's a funny looking G, but that's what it is. It's gamma. Other questions? All right. And notice there that if you have a positive unit vector component, the inverse cosine gets you an angle between 0 and 90. If you have a negative unit vector component, when you do an arc cosine, you get an angle between 90 and 180. That means it's going in the negative direction with that angle greater than 90. Okay. So we doing all right with that? We good? Yet another process there, okay.
If gamma is in the negative zone, can you just use arc cosine? We still get.
Let's see, so what we got going on here, we got a negative unit vector component. So that means it's going down essentially, as Z up and down. So when you do the arc cos of that angle always comes out to greater than 90, because from the positive 90 gets you flat in the xy plane, so greater than 90 gets you negative. That's the relationship. And it just kind of comes out in the wash, I guess. All right. All right, why don't we take a break here? Are there any other questions, though, I guess? Any other questions? Are we doing all right?
I have a-
Yeah, what's up? Question?
I have a question on like the homework we just reviewed.
Um,
Can we go over that
I could take a quick question on it. I mean, I could
I
go.
just have trouble finding like the angle for,
Okay. Well, we can maybe, why don't we just look at it during break?
Okay.
That might be the easiest thing to do. All right. So, all right, so we'll take a break here.